Well, thank you very much, Anastasia. And
sorry, it's something that they did. I don't know why they did.
No, it's fine.
Yeah.
Sorry. Well, anyway, thanks to Anastasia, and thanks to the organisers for allowing me to speak on this work here. So this is, I'm going to talk about joint work with Tim Adamo and Atul Sharma. And so most of the talk has already appeared in this in March, but the last little bit, the last couple of slides is a forthcoming paper, which hopefully is not going to take too long, although at this stage the ideas are a bit open-ended. The idea of this was to revisit some work that David Skinner and I did back at about 13 years ago. That was meant to be a space-time derivation of the MHV formula for gravity amplitudes, and is really revisiting it in terms of sort of developments that have happened since then. But one of the messages of this talk is that the derivation is meant to be coming from twistor space via null infinity, and it's twistor space which is the natural sort of geometric location of W1 plus infinity symmetry. So I got very excited by Andy's paper when it came out, and thought, oh well, that's that's very much the sort of thing that we are or ought to be experts on. And I discovered, of course, that I'm not really. But anyway, so I want to talk about how our twistor models relate to that was the final where I want to get to in this talk. But basically, the connections involved are going to be via, so this is of course a celestial conference, and we're talking about understanding amplitudes via null infinity in sort of terms of holographic models at null infinity. And of course, massless amplitudes are the natural vehicle. They're defined in terms of data at null infinity, scri plus minus. And there's been a lot of holography going on since the 70s in other communities, more classical GR communities. In particular, Ted Newman had a program to try to reconstruct space-time in terms of the cuts of null infinity. So you imagine there's a light cone in the interior space-time, heads out to null infinity and cuts null infinity in some 2 surface. He kind of missed, he didn't get the original space-time, he got H space, which is a self-dual, complex self-dual space-time. And in some sense, this part of the point of this talk is going to be that is the natural recipient for the MHV amplitude. We can think of the MHV amplitude as actually being, in some sense, an amplitude that's defined on a fully nonlinear self-dual spacetime, and that's why the formulae are so neat at MHV. But even better, rather than work at null infinity with Newman's good cuts, you can work with twistor space, and the origin of Penrose's nonlinear graviton construction was Ted Newman's good cut equation, and it was a reinterpretation of that equation in twistor space. And I'll talk quite a lot more about how that correspondence worked. Part of the point here is that twistors are non-local in space-time. They, in some sense, correspond to 2 planes in the complex that do reach out to scri, so you can access them at null infinity. And twistor space, like scri, twistor space is a 3-dimensional space that describes 4-dimensional physics, so it still has a holographic aspect. And in some sense, what I'll explain is that there's a kind of a Legendre transformation between sort of null infinity and twistor space. Okay, so there's quite a lot of material here, and I'll skip over some of it quite rapidly. The first item that I'll skip over rapidly is how to get a generating functional for the gravity MHV amplitude from just regular space-time Einstein-Hilbert action, but via various ideas of Babansky. In fact, 2 different sets of ideas: his action for his version of the Einstein-Hilbert action, and also his Babansky scalar for self-dual backgrounds. And then I want to, just to emphasize the connection with null infinity, I want to explain how Newman's H space and good cuts of scry relate to the asymptotic twistor space and Penrose's nonlinear graviton construction. And then what's one of the new ingredients of what we do is to introduce a sigma model in this twistor space, which also relates closely to a sigma model that actually describes these good cuts of Newman. And what we'll do is we'll show that that actually gives rise to this, directly gives rise to this Plabansky scalar and the Plabansky space-time action. So this is a direct connection between the space-time action and tree formulae for scattering amplitudes, at least at MHV. I'll skip over, but sort of briefly mention the way this extends to the full gravity tree S matrix, but that will actually connect perhaps rather better to sort of Song's talk on scattering equations and stuff. And then finally, I want to talk about the L1 plus infinity symmetry, LW1 plus infinity. Okay, so so just as a very brief reminder, I mean, to this audience, hopefully I don't need to sort of go on about this too much. Our amplitudes can be functions of momenta that have been decomposed into a pair of spinors, be dotted and undotted, and we have the standard spinor helicity notation for such things. And so the thing that was new from the 2008 paper, where David and I were trying to construct the MHV amplitude, back then we had the BGK formula, which was a bit of a mess, to be honest. We liked it at the time, and we had our own formulation of it, but it was a mess. But Hodges in 2012 came along and found this beautiful determinant formula, whose entries are just these simple ratios of sort of spinor contractions with this sort of diagonal entry, which and so that I'm abbreviating a bit here. And in fact, Bo Feng and Song He showed rather beautifully that this actually has an alternate interpretation. It's not just a random determinant, but it can be related to a sum of tree diagrams via the matrix tree theorem. And this had actually at the time been recently just rediscovered by the Brown group, but in fact it had appeared sort of some 10 years or 14 years earlier in work of Byrne, Dixon and friends. So anyway, so part of the point of this talk is to explain some of that. And okay, so as I say, I want to explain how it comes from the Einstein action. And so I'll skate through this rather fast. If you set up a frame rotation, frame formulation for your metric, you can write down the Einstein-Hilbert action, just as integral of the scalar curvature, as in terms of the curvature of the self-dual, anti-self-dual, sorry, I always get confused, spin connection. And so the point is that in this format, this differs from the standard Palatini action by a term that just happens to vanish and on shell. And this format gives you a rather nice method for perturbing around the self-dual sector. So in the self-dual sector, gamma is equal to 0. You put your coupling constant here in terms of the gamma-gamma term and put kappa squared equal to 0. And then suddenly you get this expression here, which is the action for the self-dual sector. You find that the two forms are closed, exactly closed. There's no anti-self-dual spin connection. The metric is self-dual, and the gamma still lives, and it's a linear field on the background. And then if you want to reconstruct the full gravity, you need to throw in this extra interaction term. And that interaction term naturally gives you a generating function for the MHV amplitudes. These two are anti-self-dual, and so that's the minus minus in here, and there are linear fields on the background, and there's this sigma is self-dual background field, and this E plus then is a functional in the sense that if you expand this self-dual field in terms of lots of little gravitons, you'll get the MHV amplitude. And you can interpret sort of various standard law about sort of the all plus amplitude vanishing and so on in terms of this. So scasing on through rather fast, you can, so this was the formula that David and I were using 13 years ago, 14 years ago. And we had a little bit of a problem with it because when you put your momentum eigenstates in there, because it's a connection form, it has a bit of gauge freedom left in it. And so all of our formulae back then had some gauge freedom left in it. And and what we observed this time around in this revisiting was that when you have a self-dual background, so we can use the two momentum spinners of the two minus helicity particles to set up this Plebanski scalar version of the self-dual background. And in that, the self-dual two forms naturally can be expressed in terms of just two coordinate two forms of the x and the x tilde associated with the two different sort of momentum components. And then the only complicated part is the middle self-dual two form, which is a Kähler two form in these kind of complex coordinates in terms of this Plebanski scalar. And then
Eleni, I think Andy has a question.
Oh yeah, sorry, hi.
Could you just comment on how do you think about the fact that you have one minus in a theory with self-dual theory where the linearized excitations should have only plus, or one self-dual when it's a theory in which all linearized excitations are anti-self-dual, or the other way around? You've only got one kind of duality. So how is it you're having amplitudes with fields of the other duality? So
we're not working so what we're doing is we're working in Einstein gravity, where there are both helicities available, and we're expanding around the self-dual sector. And in the self-dual sector, the plus gravitons, they have no inner product with each other. It's a kind of, or at least the symplectic form vanishes on the self-dual sector. So to get a non-trivial inner product, you have to have minus pairing with a plus. So
you would say that the amplitudes for the pure self-dual theory all vanish. Is that?
Yes, and I guess here what's happening is that in fact, because in order to get a non-zero amplitude, you've got to have a plus and a minus to get something non-zero. And that's and so just the fact that the self-dual sector is consistent as a subsector means that no minus amplitudes are created, and so you just get a zero amplitude. But that's because I'm looking at the amplitudes in the inner product that's natural for the full Einstein-Hilbert action, and that there are actions that people study for the self-dual sector which are rather different, which I guess you can write down an action for the Plebanski equations, the first and the second kinds, and I think people like Kevin Costello, David Skinner, and Roland Bittelstern, and Atul Sharma actually are studying these. And in that theory, there is a non-trivial inner product between two different plus amplitudes. And so you can start talking about the quantization of the self-dual sector in those theories. But that's not the Einstein-Hilbert action. That's some different action, which is, yeah. So I don't know if that makes sense. Yeah. So here we're working with the Einstein-Hilbert action. Okay, anyway, just to get to the main prize of this slide is this formula here. This is meant to be a generating function for the MHV amplitude. So you have the two minus particles that are explicit linearized fields with these momenta here for gamma 1 and gamma 2. And then all the self-dual plus particles are encoded in the omega. And that's this Plebanski scalar. And then at that point, this is something that satisfies a complicated nonlinear Monge-Ampere equation. So you're not going to be able to compute that with ordinary perturbation theory on space-time without a great deal of luck or skill. But the point here is that we can generate it from twistor space. And so I'll go on now to describe that. Okay, so that's meant to be the takeaway there. So just to talk about cuts of null infinity, I've tried to do this in a kind of weird hybrid set of conventions, which I hope are not too, doesn't alienate everyone, where I've decided to use Bondi coordinates at Scri for which the cross sections are actually planes rather than spheres. And the simplicity there is that you can represent the cut of a light cone of a finite point x in flat space just as this simple kind of quadratic expression in terms of the coordinate z, complex coordinate z on the plane. And this has this nice, rather more Lorentz invariant spinor formula here if you write out that complex coordinates in terms of a spinor. So what Newman did was he wanted to sort of do this in the nonlinear regime. So suddenly now using similar conventions, we're talking about a fully curved space-time, and you rescale the metric. And having been brought up in the Newman-Penrose school, I'm just allergic to calling this asymptotic shear C. So I apologize to those who have been working from Bondi and Sachs and so on. So this sigma naught is usually called C, Z bar, C bar, Z bar, Z bar or something. But this is the asymptotic shear, and it's the asymptotic shear of the cut of Scri U equals constant. So just as you get out to infinity, this thing is shearing. And Newman's good cut equation was trying to get rid of that asymptotic shear. We try and choose a cut U as a function of the round coordinates Z, Z bar. So if that kills the shear, then it's a good cut. And in fact, if you put your split signature spectacles on for a moment, so Z and this little Z and Z bar become independent, then this is just a second order equation for Z, and this is a geodesic equation in the Z bar direction. So what a good cut is then is that it's a cut of Scri that's ruled by null geodesics, but in the Z bar direction. And this gives an elliptic problem for two surfaces in Scri. You have to complexify in U because this sigma here is complex, so Z has to be complex in order to solve that equation. And but this equation, by virtue of the second order equation in Z bar, it's linear in Z bar. And by globality, by a version of Liouville's theorem, it ends up being linear in Z because this is a kind of all line bundle values, which I've sort of suppressed. And the way I like to put it is to say that we have this, these are kind of somehow coordinates, and then this M here is a perturbation. So this M is uniquely prescribed, uniquely defined, given these four coordinates. Anyway, so these four coordinates then I'll just write as that little x there, and Newman proved that they have a four-dimensional space of solutions, which is actually a nice space-time, a complex four-dimensional space-time, and it has a holomorphic self-dual Ricci flat metric G+. So this is going to be our self-dual background that describes the self-dual perturbations in our symmetry formula generating function. Within the year, Roger Penrose reformulated that in twistor space. And in some sense, this isn't so difficult from the perspective of thinking about null geodesics in complex Scri or split signature Scri. As far as Roger was concerned, the asymptotic twistor space is somehow, well, he didn't say it like this, but you can say it by saying that it's a phase space description of these null geodesics. So you turn that second order equation for the null geodesics in the Z bar direction into a first order Hamiltonian equation. And in order to do that then, this lambda is essentially going to be the same as the Z coordinate we had before. And the mu is going to be first order equation. So it's like the Z and the d by dz bar of Z the Newman's good-cut equation, and being a phase-based description for the null geodesics, you have a Poisson structure, and this is what the Poisson structure looks like. It's just it's essentially the Wronskian of the good-cut equation. And yeah, and if you're not thinking of it with split signature, then the way that you think about the good-cut equation, then sorry, if I go down here, the good-cut equation now is a first-order equation on these mu's. So this, and it's a Hamiltonian sort of equation because we're going to a kind of phase-space version of the story, where this h here is just an integral of the asymptotic shear. And this defines a complex structure on the twistor space. So if you have a function f of these w coordinates that's not necessarily holomorphic in w, then sorry, that was d bar sub h of f is the flat, I'm missing my f there, flat d bar of f plus the Poisson bracket of h with f. And so this is a description that George Sparling came up with back in the 70s, or connection between the Newman and the Penrose versions. Anyway, so I'm going to straight away lift this to lift the good cut to the twistor space then, with this kind of slightly weird coordinatization. So actually, what I'm going to want to do is I'm going to want to put homogeneous coordinates on the cut. They're related to the z coordinate around the celestial sphere by z is therefore sigma naught over sigma 1, but I'm going to give them an inverse relationship with the lambda coordinate on the twistor space. Everything actually has weight -1 in these homogeneous coordinates. And then this kind of perturbation away from the flat case is going to be given by this capital N here. Anyway, the good cut equation now is this d bar equation that tells you that the complex curve inside this deformed twistor space has to be holomorphic. And that equation comes out like this in terms of the Poisson bracket. Okay, so so we can write down actions. Well, this is really in some sense a null geodesic action in the z bar direction, but we're now thinking of this as a sigma model action for the good cut. This h here is just, as I say again, the integral of the asymptotic shear, and so we can do a sort of a Legendre transformation again from this kind of Lagrangian for the null geodesics in the z bar direction at scry to this description here, but now we're thinking about it as a sigma model action for holomorphic curves in the twistor space. And so a key proposition at this point is that the value of this action matters for us in our story. So I'm not going to go through the proof of this, but given the way we've set up our problem with mu equals that plus m, so these are the same x coordinates as I had before in x and x tilde coordinates as I had before in the Pavansky description of the self-dual background. So we can use those coordinates and use the Pavansky description. And you can just differentiate this action in the x and the x tilde coordinates. And you discover after some manipulations that the derivative of this action can be related to the derivative of the Pavansky scalar. And so you arrive at this formula for the Pavansky scalar. So the upshot of that then is that the MHV generating function can be expressed in terms of this sigma model. And so with that then we can sort of start expanding in the H in the background. This H here was the data, is the as I say, the integral of the asymptotic shear as infinity. And we can expand that in momentum eigenstates. It so happens they're given in terms of these rather elegant little delta functions. And and when you expand the sigma model action, you can use elementary quantum theory. This is an on-shell thing. This is a classical statement. We're not doing any quantum theory here. So what you actually need to get is not the full quantum correlator of a bunch of vertex operators, but a tree correlator. So that is to say that the value of the on-shell action is equal to on-shell tree diagrams on n-2 vertex operators for this sigma model at Scry. And so that's really made out of contractions between these expressions here for the momentum eigenstates, and that immediately gives us the entries in the Hodge matrix. And these tree diagrams then can be shown to be precisely the tree diagram formalism of Byrne and friends, and you can follow Bow and Song to show that the matrix tree theorem gives rise to Hodge, the Hodge determinant or reduced determinant. Yeah. Okay, so where am I? And I've got a few minutes left, I guess. Good. So maybe in order to, maybe I should just pause for questions there though. So this is the kind of main result, I guess, of our, or it's the first main result of our and yeah.
Yeah, I'm not sure which 1998 paper, Byrne et al. You're talking, but in that paper they also had loop diagrams, which were, or some paper in 1998. They
I've been
had,
meaning to. I wish I could give you a good answer to that. I've been meaning to sort of study those, and also Bow and Song studied those as well in terms of the matrix tree theorem.
and they're supposed to be, they're all plus, right? They don't have the.
That's right, and they, yeah, they have the same status as the one loop all plus amplitude. So I guess, if I, no, but that's a lovely point actually, and I mean there's a more elementary example of that, which is the all plus amplitude in Yang-Mills, which again, using ideas related to this, I've always hoped to understand it. So you can write down, in that case, you can write down a beautiful generating function in twistor space for those. But I've never had a kind of ab initio derivation of that. And Assel is telling me. Yeah.
There's a generating function in twistor space for the all plus loop amplitude?
Yeah, I mean, this is something that I didn't write it up myself, but Rutger Bowles put it into a paper from 2006 or something.
And is there a loop calculation in the from the?
No, I mean that's what we're missing. So yeah, Assel was telling me this is the project I should be giving to my new research student this year, is to sort of really. We probably know enough now to try and pin down some of these ideas. But it'd be lovely to do that Yang-Mills case, and of course this Byrne-Dixon, Perelstein-Brzozowski one as well. I mean, that'd be a beautiful thing just to understand from some first principles.
And could you just summarize here how many dimensions? I always get what's real and what's complex, and is this a statement about, can this be a precise statement about 2-2 where everything is real, or
the connection to 2-2 signature is something where there's quite a lot in the literature, and I could talk about that, but you always need the Riemann sphere or a disk. And so what happens in split signature is that in fact you have a totally real part of the twistor space, but rather remarkably, the full complex part of the twistor space happens to exist too. And you end up looking at holomorphic disks inside that twistor space with boundaries on the real part. So you end up with an elliptic problem again. And this is something that I studied with Claude Lebrun over many years. And there is a very pretty story there, which is more like an open string story.
I see.
But that would be a different sort of.
But here we're in 4 complex dimensions, or we're in 4 real dimensions with complex field, or where are we?
Okay, so I mean, I quite like to go back to the Newman's original perspective, where he was really starting in the rent signature and then was just forced to complexify just in the u variable at null infinity, not the z or the z bar, just the u variable. And so you do need to do that because the good cut equation is a complex equation and it's for u equals z. So this formalism really does sit very nicely into a kind of an analytically extended Lorentzian rather than split or otherwise. In split signature, you really need to change your perspective as to what's going on quite completely.
Thank you.
Okay, so I'll skip over the higher MHV degrees. Higher MHV degrees correspond to higher degree in twistor space, as familiar from twistor strings and various other places. And you can get a formula which you can prove using this sigma model, prove using the Kashaizo-Skinner formula. Sorry, I've only got about, Anastasia will tell me I've got minus something or 2 minutes or something. But anyway, okay. So what's the point? The point is that the W1 plus infinity algebra, just abstractly, is a story about Poisson diffeomorphisms of the plane. And the plane here in question is the mu alpha dot plane in twistor space. It's a kind of, as I say, the Legendre transform of the lambda equals constant planes on scry. Sorry, the z equals constant planes on scry. If we just reformulate the twistor sigma model in terms of this mu coordinate, you take out the x and x tilde, all that happens there is you add some constant to the action, so it's not a big deal. And then in terms of this action, if you have two functions on twistor space, f and g, then their OPE relative to this action is precisely the Poisson bracket of that mu plane. And then, of course, this action here is a gravitational action, essentially. The H, it describes the black background deformed complex structure. And there's a gauge symmetry under coordinate transformations here. But because we've fixed the Poisson structure, we've fixed the form of the Poisson structure, then it's the residual gauge freedoms are Poisson diffeomorphisms. And they can be thought of as G, which are functions on twistor space, but they may have some anti-holomorphic dependence too. And under that, then everything deforms according to standard Hamiltonian transformations. And then this H transforms under D bar, this D bar of G. So if you want it to be a genuine symmetry, then delta H should vanish. And then if so, D bar of G should vanish, so it's holomorphic. And if G is global, then that's Poincare in the flat space, and of course there are no symmetries in the curve case. But a weird thing happens if it's local. So if it's local, then G has singularities, fine, so it doesn't extend everywhere. But the charges for G, well, they can still exist. You can still do a contour integral of G on your holomorphic curve for this sigma model. And it turns out that that's the same as, roughly speaking, the integral of D bar of G or something, and this is the formula we had for our gravity vertex operators. So we have this kind of interplay between local symmetries and gravity vertex operators, and this is actually a version of the Čech-Dolbeau isomorphism. I've been giving you here a Dolbeau presentation of the twistor space, and whereas we wanted a Czech version. So just to see that in the case of the momentum eigenstate, the Czech version here is given by this. You do D bar of that, and you get the delta function at lambda equals K that we had before. And so now we can sort of make this correspondence a bit more precise with this Czech version of the momentum eigenstate. So that's just a statement that it's D bar of it gives the what we had before. But now if we do the Mellin transform and then the soft expansion in omega, that just gives you the powers in this mu kappa tilde. And you can relate that directly to Andy's presentation of the loop algebra of the W1 plus infinity. and complete with combinatoric factors. So this here now, these are now polynomials in the mu. And if you, well, I'll put an extra index here just because what we've got is a loop algebra, because you've got some Laurent series in lambda. And then the plus and brackets then land on Andy's formula, except with the extra loop algebra stuff. Okay, so just to finish off then, gravity tree amplitudes are generated by the on-shell action of this sigma model, and the degree of the map corresponds, the degree of the map corresponds to the MHV degree, and it sort of gives you a kind of rational approximation of the true light cone cut. And the geometric action of the W1 plus infinity is by check vertex operators for self-dual gravitons. You're really identifying the self-dual graviton phase space with the loop group LW1 plus infinity. I mean, there's maybe a little bit of slop here and there, but that's what we're doing. And this goes all the way back to Roger Penrose's original article, where he showed that you could glue together the nonlinear graviton with a generating function for the expressed in terms of area preserving diffeomorphisms in the complex. And so this soft graviton expansion then, so this is a correspondence, which is, there's nothing soft here. But if you expand around the soft sector, we just get the standard mode expansion for this loop, the loop algebra W1 plus infinity. If you want to extend beyond self-dual sector, everything lifts and embeds into the 4D ambi-twistor string. And there are various extensions here. I just want to give a bit of a plug. I like the direct relationship with the Einstein-Hilbert action. It only occurs at MHV, but I want to give a plug for Attal's paper here, where he now can do that off-shell all MHV degrees. So that's something, well, okay, there's no connection with Amplitude yet there. I mean, there's a lot of work to be done on this, but it's that's a step forward. I think I've run out of time to say anything about quantization, but we have a kind of a formula that we don't know how to parse for the quantum correlator. Does this have anything to do with anything? We don't really know. And Moyal definition and palatial twistors are things we've discussed over the years, but I better, before Anastasia tells me to shut up, I better stop and say thank you.
Okay, so let's thank Lionel. Now we have some time for questions. Actually, can I just ask, could you like make precise statements for this W symmetry? Like you have an action which realizes it. Could you just make one sentence statement of how this algebra arises in your construction?
Right, so
just one sentence. You have an action which, or what do you have? Sorry.
You see, I think the actual correct statement is, I hesitate to call these symmetries here because
let's call it, let's take this algebra as a given. We have this algebra, okay, we have commutation relations, right? So what do you have now?
Okay, I think if you just go to this statement here, this is the statement that I would want to focus on. So Penrose's nonlinear graviton construction realizes the self-dual graviton phase space as the whole of the kind of nonlinear loop group for the area preserving diffeomorphisms. That's the statements I want to make, and you can find that already in the last section of his 1976 article.
Yes, I went and read that after you pointed out to me, and there it is. I should have mentioned it yesterday. And it is the loop group of the wedge algebra, right?
Yeah, I mean, so infinitesimally, you start looking at gravitons, then you know, each check vertex operator is, each element of this loop algebra is represented by a check vertex operator for a self-dual graviton. So that's the so in some sense, you're saying that the self-dual phase space is this full algebra. I mean, it's in some sense it's a beautiful statement.
So this is for gravity. Now, I don't know if you've been to this. Castello also has something to say about some other theory. Do you know this?
Yeah.
But that was for Young-Mills. Is this related or?
So this actually goes back to what Andy was asking earlier as to sort of, is there a self-dual theory? And the answer is yes. And if you go back to the Pabansky generating function, that has an action which you can easily write down. So it's a Monge-Ampere equation. So that was the determinant of d tilde of omega equals 0 is the equation. You just put omega in front of that and you get an action. So you can write down an action for that, and then you can say, can I quantize that? And then in that action, self-dual modes had non-trivial pairing with each other. In the Einstein-Hilbert action, two self-dual modes vanish when you kind of take in the products of them with themselves.
But that action is not Lorentz invariant.
It's absolutely not Lorentz invariant, that's right. And so what you've done is you've chosen that sort of that Kähler structure for the background, which for us is coming out of the two minus gravitons. So the two minus gravitons are choosing the x and x tilde coordinates, which are giving us the kind of Kähler background.
Oh, in the plus plus minus amplitude is the LW1 plus infinity acting on the plus or the minus?
Sorry, in the plus plus minus amplitude.
Can you have two of your graviton vertex operators that create the charges?
I think
Are your graviton the perturbations or are they the part of the self-dual background?
So the minus ones are giving you the kind of, so you need two minus ones to give you the kind of Kähler structure. So somehow how one of them gives you the x coordinates and the other one gives you the x tilde coordinates, and you're thinking of them as, in some sense, like complex conjugate coordinates on space-time. And typically, if you look at the plus plus minus amplitude, that's kind of local on twistor space and disappears as soon as you look at it. It's a kind of you know, certainly if you go on shell, it disappears. Whereas the minus minus plus does not disappear. That is already realized here.
So you're adding two sources, not one.
Yeah, so I guess the point is that the single minus all plus amplitude, you know, one minus and rest plus amplitude vanishes, because that's a statement of integrability, because that's a statement that if you take a plus particle and you scatter it through a plus background, it doesn't change. The minus particle in a product would measure the change of the plus particle moving on the plus background. So that's a statement of complete integrability of the plus background.
More questions?
Okay, so then in the Byrne paper, they have, okay, this is convention, but I'm about to say something which isn't a convention. They have, when they're studying, they have minus plus plus, they say, and then they at one loop get all plus.
Yeah, so that's actually telling you that in some sense, the self-dual sector is kind of anomalous at one loop, which is a kind of a weird statement. You know, there is no such thing as a self-dual sector if you in the quantum theory. So, I mean, we do need to find a way of understanding that cleanly.
You can actually couple it to self-dual Yang-Mills for SO8, apparently, and make it non-anomalous. That's Costello's discovery.
Oh, is that right?
Yeah.
And then do the all plus amplitudes vanish?
I haven't checked, but I don't think they would vanish. I think his anomaly cancellation, he checked only at the level of the 3-point vertex. I don't know if he computed the all plus amplitude at one loop.
I mean, the comparisons.
So there should be two W1 plus infinities, one for the holomorphic and one for the anti-holomorphic. And it's possible we're actually studying the opposite ones. Okay,
Yeah, so
we should probably understand this offline, but I think we might be studying the opposite ones.
I think in some sense they're the same, but I mean yeah, I mean you can lift everything to the 4D ambitwistor string, and you do it in a way that somehow preserves the Poisson structure, and there you can see the complicated interaction between the self-dual and the anti-self-dual W algebras. So there's a W and a W tilde, I guess, but
yeah.
That may be not what you're saying, but I think that what we've done, I mean, you know, we really line up. Sorry, I guess my notation is a bit different. I mean, I think the kappa tilde here would be Z in your paper. Sorry.
While you're on this slide, could you tell us exactly what your VHK depends on?
Which depends on, sorry, the V.
You have on the second bullet, you have a VHK, a graviton vertex operator.
Oh yeah, right. The graviton vertex operator. I must have had it a couple of.
Yeah.
It's at the end.
So it would look like that's what it looks like. It's a delta function supported at, well, this is really, instead of lambda, that should be Z equals kappa, and then there would be an omega up there in your notation. Actually, sorry, this here is, I realize I've got the wrong one there. Well, it's fine. It doesn't really matter. It would look like that anyway. So the H kappa is this here is a homogeneity to self-dual one that. Sorry, yeah. Yeah, so it's expanding out in this kappa tilde that gives lots of nice combinatorial factors that line up with your combinatorial factors to express the G in terms of the W's.
Yeah, that's probably the most beautiful thing, that you basically just do binomial expansion of this mu kappa tilde by just setting kappa tilde to 1, z bar in 2 signature, and then you do binomial expansion to get these generators like in mu naught dot to some power, mu 1 dot to some power, and you get your gamma of p minus n, gamma of p plus n, those light transform factors. Those gamma functions that were generated by the light transform, literally just generated by the binomial expansion here.
So would it be possible to simply, write G mu nu equals eta mu nu plus H mu nu, where H mu nu is a graviton of a solution of the wave equation of some fixed chirality, and actually write down an explicit formula for these VHs in terms of that without complexifying or, sort of boil this down?
The way you'd usually state it is that there's an integral formula which would take you from H mu nu equals an integral. Sorry, the variation in the metric is equal to an integral of roughly speaking 2 derivatives of H. I mean that's the way you'd usually do it. 2 mu derivatives of H.
That's the Uguri-Waffa style description. You write the metric as eta mu nu plus some scalar perturbation. Is that what you described?
No, the Kähler, that form is a little confusing because it's a manifestly, it's not Lorentz invariant. That's a very awkward way to do it. I mean, at the end of the day, the formulas that you get that way are highly non-transparent, I think. But there should just be some formula. We should be able to, these things generate, these charges have an algebra and they generate some symmetries. And so we should be able to write them as we have some solution of the linearized wave equation for H. And we take the Klein-Gordon inner product of that with the field operator. And there's some particular mode with some particular properties that is the charge.
Yes, I'm wondering if we could.
And at the end of the day, you should be able to just write that without complexifying or with, I mean, it may be that this is the fastest way to get to that, but at the end of the day, one should be able to write it down without using all the formalism, I think.
Yeah, I mean, you shouldn't, I mean, these integral formulae for linear fields are kind of quite uncontroversial as far as complexification is concerned, and they
Right.
And I guess you're asking an interesting question as to whether you could somehow you factor the essentially the Poisson structure on twistor space through the integral formulae. I mean, I guess that's interesting. So you
Well,
can actually
we have papers in our formulas in our papers where we just, we've just solved the wave equation, and
Right.
we've solved it with some particular quantum numbers, and they're formulas for the components of H mu nu on space-time, and these are, and they obey this W algebra, though I'm not sure if it's the same one or the other one.
Well, I mean, there's a possibility for confusion here, you see, because I think I get confused whenever you ask these questions, because you could re-encode the algebra on the kappa tildes instead of on the mutes. I think Chris is telling us we have another talk.
Yeah,
Sorry.
okay. Andy and Lionel, I hate to do this. I'm very sorry, but we're 15 minutes over time, and I got several from the organizers. Several texts I have from 2 organizers, so 15 minutes.
I'm sorry.
No problem. Why don't we continue during the break, this discussion, because we have to make it on time for Henrietta. We're already 15 minutes over time. So thank you so much, Lionel, and I apologize for cutting this short, but we will continue this discussion during the break. So let's thank Lionel for a very nice talk, and move on to Song Hee, who will share a slides and
Can you make the other, like my iPad, to be the co-host? Because I'm
right away. Yes, just give me 1 second, please. You are on another one. It doesn't appear.
Just Song.
Song. Okay, yes, it's under a different name. Okay, got it. Thank you.
Thank you.
Host. You should be all set now.
Great, thanks.
Can you share your slides?
Now.
Can you see it?
We don't see the title page, yeah. Okay, so our next speaker will be Song Hee from Beijing. He's going to tell us some comments on scattering equations.
Thank you. Yeah.
You have 30 minutes. Okay.
Yeah. First, I'd like to thank the organizers for the invitation and organizing this wonderful workshop. So I'm not going to talk about celestial amplitudes today, but I think I'll just give some, as Stefan actually asked me to give some comments on several topics which are closely related to scattering equations. And I hope for people who are not very familiar with this topic, you probably learn 1 thing or 2 after the talk. And also for the experts, maybe staring at all these familiar formulas, we can inspire some new discussions. Okay, so let me start. this is the scattering equation that I'm going to talk about for n massless momenta, which you can write as k1 through kn. And what appear in the scattering equations are the Mandelstam variables of this k plus kb squared, or the Lorentz product of k dot kb. And these are equations for all the n punctures z1 through zn on a Riemann sphere, or M0 n. And so you provide some any kinematic point. You want to solve this n equations for this n punctures. And these equations are actually just the saddle point equation for any string amplitude for the Cobalt-Nielsen factor of the string amplitude. So they actually appeared in the early days of the dual resonance model, also appeared as in the work of Gross and Mende, but it's only like 7-8 years ago that we realized these equations play important role for scattering of massless particles in quantum field theory. So let me just remind you how this equation appeared. So they were actually the generalization of what Witten has written down, and also by the work of Roybens, Brodny, and Bolovich as the RSV equation, which works in 4 dimensions in terms of spinor helicity, but now generalized to general dimension in terms of this Mandelstam variable. So the key idea is that you can consider some one form, where this one form is just a linear combination of this d logs by this momenta. So this one form has the property that if you essentially evaluate the z at any puncture za, so what you literally do is do a contour integral around za, it gives you that particular momentum of that particle. Okay, so the first consequence of this is that you see immediately that in this construction, momenta are conserved. So this is the fact that momenta are conserved is the fact that this form has no pole at infinity. So you want to ask this form had no pole at infinity. This tells you momentum conservation. So this is very simple. But then you ask something a little bit strange actually. So you want this one form to be null everywhere. For any z. So basically you want a map. So you want this one form to be a map from CP1, where you have where z is at, directly to the light cone of your momentum space. Okay, so you're not just asking it to be null at positions at these punctures. You're asking it to for any value of z, you want it to satisfy this null condition. So translated in, you just plug it in, you get this form, and of course at this position a equals b, the double poles, this tells you the null condition for your external momenta. But also at each simple pole, the more non-trivial constraints that you have this scattering equation. Okay, so you can view scattering equation really as some consistency condition for you to be able to construct such a map from CP1 to the light cone. Without the ZA, without all the punctures satisfying this equation, you won't be able to do that. So that's really where this comes from. Okay, so this provides you immediately some connection between the moduli space, where all the M0n, with what I call the kinematic space of m massless momenta, which are just spanned by this Mandelstam variables modular momentum conservation. So this connection is something we're familiar with even in string theory, but now in the context of these equations. So basically, the equation connects these two spaces, and whenever you have some degeneration happening for your modular space, namely the Riemann sphere got degenerated into products of Riemann sphere with less punctures. So you have also like common punctures at where they intersect. So these are what happens when you degenerate your modular space. Whenever this happens, the equation just related to a configuration where in kinematic space you have some Mandelstam goes to 0. So exactly the Mandelstam of those particles that belong to either one of the two smaller sphere. So basically each degeneration corresponds to a factorization in the kinematic side. Okay. And also a quick comment is that here you don't really have any equations, n variables, but rather just n-3 equations for n-3 variables because there's an SL2C. And also there are n-3 factorial solutions if your kinematic is generic. So basically this can be nicely seen by a soft limit argument. Let me just quickly go over it that if you take one of your particle to be soft, then the scattering equation for all the remaining particles, they just become the equations for n-1 particle system. So basically your particle end job in this soft limit in all other equations. But then for the last equation, you have equation for your last variable Zn. Everything is finite here when you factor out the epsilon. And now this is the equation of degree n-3 for the last variable. So this is what tells you that for every solution of n-1 particle system, you have n-3 solution for the last variable. So that's how you get n-3 factorial solutions, at least near the soft limit. And you can actually use this to go to generic kinematic point to get still have this number of solutions for generic case. Okay, so these are just a quick review of what scattering equations are. And now I want to tell you three comments which are more or less familiar to some of you, namely soft theorems and amplitude relations, including double copy, and also the connection to positive geometry. Okay, so in the end, I'll also go back to 4-dimension and some other special dimensions where I think things are even more interesting. So we understood things actually better in D-dimension, but less well in 4-dimension. So let me start with soft theorems. I mean, this is when you already have your scattering equation, you can write down this CHY formulas where you have your measure, which is just integrating in your modular space with this delta functions imposing the scattering equation. So these are n-3 delta functions imposing n-3 independent scattering equation, and then I have some what we call the CHY integrand here. Okay, so these integrands, they transform under SL2, what I call weight 4. They have weight 4 under the SL2 transformation, which naturally asks you to actually view it something like a heterotic string where you have left mover and right mover both carrying weight 2. So this there's all these CHY integrands that you've seen for various theories can all be derived from some worldsheet model. So from this ambitwister strings that Lionel and collaborators developed, and in particular, this I left and I right are all correlators on the worldsheet. And I want to derive soft theorems here as general as possible. So what I want to look at is first at the measure. Okay, so this is in the original CHY paper that the first thing you'll notice is that when you take the soft limit of a particle, the measure actually factorizes quite universally. By factorize, I mean the measure becomes the measure of n-1 particle with this last integration, where this integration is a contour integral that I just write the last delta function as a pole, and I need to enclose this pole. Okay, so this is independent of any theory. You just have this general soft behavior of your measure. And now, if you want to have some soft theorem for theories like gravity, Yang-Mills, and so on, you need your CHY integrand, or actually each of the correlator, I left or I right, to behave like that, to also factorize into n-1 particle guys times a soft factor. And this is nicely the case for essentially all the half integrand we studied. For example, the famous Park-Taylor factor, which is needed for any particles with color or flavor structure for given ordering. This is the Park-Taylor factor. You don't need to take any soft limit. It's just literally the n-1 Park-Taylor times this soft factor for Park-Taylor. Okay, so just the Zn1 minus the difference of this to 1 over Z with adjacent particle 1 n-1. And then the more non-trivial one for the this so-called Pfaffian factor, which are needed for gluons, each copy for polarization spin one particle. They are essentially given by correlation functions of vertex operators in type 1 theory. Okay, so they can be written nicely as a Pfaffian, and in the soft limit, it does factorize into n-1 particle Pfaffian times this factor. I just want to, I mean, this everything here is very well known, but I want to draw your attention to these soft factors in the worldsheet quite universally for the color part and for the polarization part. Now, there is a third case actually. If the particle you are studying are Goldstone particles, then they tend to go to 0. So there is this building block for all the Goldstone particles that they just as the particle goes soft, this guy just goes to 0. Of course, you can study what's the next order in this. What is the coefficient of this 0? But for our purpose, this will be what's responsible for the Adler 0. Okay, so now you can collect this ingredient and study soft theorem nicely. So for example, for the graviton case, actually not only just for n graviton amplitude, but you can make the argument even more generally that for graviton interacting with other particles, it always factor out this 2 copy of the this Pfaffian soft factor that I mentioned, right? So in the particular n graviton case, this is just because you have 2 copy of Pfaffian, so you have this guy squared, and then remember you have this contour integral that asks you to enclose this pole, but you use a residue theorem to enclose poles here, which give you the famous Weinberg soft factor. So this literally come from this worldsheet soft factor, the actually double pole of this worldsheet soft factor, because here you have some simple pole, so you need double pole to really get contribution. And you can do similar but more complicated argument by expanding to next order to get even subleading soft theorems from this formula. But I just want to show you how simple it is to get the leading order at least. And for gluons, the only difference is that you have one Pfaffian type soft factor on the worldsheet and this guy. So now you pick out the adjacent legs to give you this gluon soft factor. And then for the Goldstone scalars, because you have different powers of this vanishing factor that I mentioned for theories like nonlinear second model, DBI, or this very, very special theory of Galileans, that you have higher and higher order Adler 0. So this is called enhanced Adler 0 for this special theories of special effective field theories. Okay, so these are the soft behavior of CHY. Let me also quickly tell you about some amplitude relation that you can derive. So actually, historically, how we discover the scattering equation is through these 2 points. Okay, so the first point is that you notice that Park-Taylor factors, if you want to ask Park-Taylor factors to satisfy so-called BCG relations, then this is actually equivalent to scattering equation. Okay, so this tells you very strongly that, I mean, the first thing that Freddie studied was in 4 dimension, that the Park-Taylor factors in twistor string satisfy BCG relation, but BCG relation should be there in any dimension. So that's why this immediately suggests that what you should be looking for are some universal equations like that. And also already in 4 dimension, there's the formula by Freddie and Yvonne by taking the KLT product of 2 copy of Yang-Mills formula. So each Yang-Mills formula is some twistor string formula, and that gives you a twistor string-like formula in gravity. And this requires some interesting property which you can prove using scattering equation in general dimension. So basically, if you take take 2 color ordered amplitude in CHY form and double copy them with KLT matrix, this immediately give you a single CHY formula where you need this. So even if you know nothing about the Pfaffian, there's just assuming this general form of a Park-Taylor times something that contains polarization, you can already prove that the gravity formula will take this form. Okay, so I won't go into the detail, but I want to say that everything about this BCJ double copy KLT relation has its root in this special theory, so-called bi-adjoint phi cube, which has a interesting Lagrangian that these scalars are take adjoint representation under two groups like UN and UN tilde. And these are just essentially the simplest theory you can imagine in D dimension, where if you strip off the color factors, you just get this what we call double partial amplitude, which are given by some combination of cubic diagrams, just some scalar cubic diagrams. Okay, and these are some matrix. This forms a matrix of n-1 factorial orderings, but you know the rank of the matrix is only n-3 factorial because they satisfy this KK and BCG relations. So the key realization in CHY is that this, being the simplest of amplitude, also has the simplest CHY formula. Basically, just take two copy of Park-Taylor factors, and that CHY formula exactly gives you this amplitude that is given by just summing over cubic scalar cubic diagrams. And you realize the KLT matrix now has a physical interpretation. It's nothing but the inverse matrix of this bi-adjoint scalar amplitude. Okay, so you go to the n-3 factorial minimal basis and take the inverse. So all the KLT formula and also the color kinematics and double copy becomes totally manifest in this way. And now you can just see many theories living in this same framework. That, for example, you have Yang-Mills, double copy with Yang-Mills, you get GR. But you also can just do dimension reduction to get Yang-Mills scalar, which if you double copy with Yang-Mills, give you Einstein-Maxwell theory. And with this dashed arrow, I mean, you can also turn on some non-abelian action here to get Einstein-Yang-Mills theory, or here just the Yang-Mills plus this bi-adjoint phi cube theory. Okay, so in this world you can have many theories with which are actually determined by gauge invariance. So this is the some very special theory, including general relativity and the Yang-Mills and their couplings. And here you also have this effective field theory world where you have your Born-Infeld and the dimension reduction give you dBi, and even there's a if you turn on some further interaction, you get the coupling of dBi with nonlinear second model. Okay, so every theory here can be obtained by double copy of the column here with nonlinear second model for the massless pions. And there are many more relations. Actually, I think some of the relations are still mysterious. So CHY makes it possible to derive them, but you still don't really understand them, say from Lagrangian or from a normal, say you don't have any worldsheet model, you still do not know really how to derive some other relations, not just the double copies. Okay, so these are the two comments I want to make that is already there 5 years ago for the soft theorem and for the double copy and other relations. Now I want to mention something slightly more recent, which is the scattering equations also provide you a natural connection to the positive geometry structure, which actually allow you to directly see positive geometry both in the modular space and in kinematic space. Okay, so we already see that scattering equation provide you some connection between these two spaces, but how do we make it more concrete? So what we need to do is actually to pick an ordering. Okay, so here you see where the positivities start to come from. You pick an ordering for your modular space, which is very natural because if you consider your real, if you consider the real case, then they naturally split into different orderings. They become, you know, ordered points on the boundary of a disk. And on this side, once you start to talk about ordering, we will see that you will be able to talk about some n-3 dimensional subspace. So the kinematic space is rather high dimension, and your modular space is only n-3 dimension. So you really need to see some subspace here to be able to make a precise map. So starting from this positive part of your modular space, I mean, it is famously that it can be compactified into curvy polytope called a social hedron, which has this many of boundaries. And all the boundaries just corresponding to your disk has degenerated into two disks with, like all the points between I and j minus 1 on this side, and all the points between j and I minus 1 on the other side. So instead of having the sphere, now you have the ordering. So all your boundaries also respect this ordering. You have this many boundaries, and now you can form a polytope. Okay. So for example, for the 4-point case, you have two boundaries, either 1, 2 on one side, 3, 4 on the other side, or 2, 3 on one side, 4, 1 on the other side. So you have a polytope now is a one-dimensional interval, a line interval whose two boundaries are just these two endpoints. And for 5-point case, I don't want to draw everything, but you have 5 boundaries where the sphere factorized into the disk factorized into 2 disks, and you can have codimension 2 boundaries where it factorizes into 3. So you can draw them more conveniently as a triangulation of your angle in general. Okay. So everywhere I have such a factorization, I just put a diagonal. So the maximal factorization, I can put n-3 diagonal for an angle. So that's why this is the polytope of n-3 dimension. So this is a famous Deligne-Montfort compactification of the modular space. Like in this 5-point case, your modular space initially looked like a triangle, but after compactification, it really looked like a pentagon because these two sides need to be blow up. Okay, so another thing you see is that after you consider positive part, then you can write down something called canonical form, or the differential form, which has logarithmic singularity on boundaries of this space, because now you have a curvy polytope, so-called positive geometry. You can consider a form which has all logarithmic singularity or simple pole on this boundary. And this form turns out to be just the Park-Taylor form. So uniquely, you find the Park-Taylor form is the canonical logarithmic form on this positive part of the modular space. So that's all for the modular space, and I want to talk about the kinematic space. So this is a so-called ABHY, a social hedron, in work together with Nima, Yontao, and Gongwang Yan. So this so-called ABHY social hedron lives in the Mandelstam space. Is also known as the amplitude hedron for the bi-adjoint phi cube theory. So basically, you have a polytope for this phi cube theory. So you have a polytope living in a kinematic space, and then its canonical form or its volume form computes the tree amplitude of phi cube theory. So let me just remind you what this polytope is. It's really a very, very simple realization, but it's a realization that mathematicians have not studied before. That I can directly realize in the kinematic space. So all the now I want to span my kinematic space not using SAB but using this Xij planar variable, which is in one-to-one correspondence with such diagonals of angle. So basically, I take the consecutive sum of momentum from I to j minus 1, square of that. Give me this this sum of Mandelstam. This is the planar variables. There are exactly n-3 over 2 of them, so they also span the kinematic space. And the ABHY social hedron is something very simple. You ask all these planar variables to be positive. Remember, these planar variables are exactly what appear in the bi-adjoint phi cube theory. If you give me an ordering, right? Once you give me an ordering, all possible singularity of your amplitude are just this Mandelstam of planar of some consecutive momenta in a planar ordering. So I ask all the singularity to be non-negative, and then I need to go to a subspace, a -3 dimensional subspace, which I define like this. So once I intersect this this region where all the poles being positive with a -3 dimensional subspace, I get a -3 dimensional polytope, which turns out to be the social hedron. So I won't give you the detail, but the subspace is just defined by some condition like that, linear combination of this X being constant. Just look at the 4-point example. If you have both S and T positive, you have your first quadrant, and this condition becomes just S plus T is a constant. So it's this line. And by going to this one-dimensional subspace, you get a line interval, which is your one-dimensional social hedron. And now you can compute the the canonical form on this line interval, which has logarithmic singularity on two endpoints, and that's exactly your 4-point phi cube amplitude, 1 over s plus 1 over t for given ordering 1, 2, 3, 4. Okay, so in general, you can find your for endpoint you have this n-3 dimensional isotropy and its canonical form give you the bi-adjoint phi cube amplitude. And having said so much, now I can connect the two. So basically, I have a isotropy living in the modular space, the positive part after compactification, and I have a isotropy living in kinematic space, which is only being constructed very recently for this bi-adjoint phi cube case. And what is scattering equation? The scattering equation provides actually exactly a one-to-one map from the positive part of your modular space to this polytope. Okay, so this is the connection between scattering equation and positive geometry. So you pull back your scattering equation to the subspace, it becomes a map to the subspace, which the image of the map is exactly the ABA tribe polytope. So this also gives you a geometric origin for the CHY formula, because once you know there's a one-to-one map, you can write the canonical form of your isotropy as summing over solution of this Park-Taylor form. So basically the phi cube amplitude as a summing over solution of scattering equation of this Park-Taylor form. That is the CHY formula. Okay, so this is how you connect scattering equation to positive geometry, and they are also naturally related to string theory. So basically, if you write down the simplest open string disk integral, where you have your Park-Taylor form and this Koba-Nielsen factor, there are two ways you can see the appearance of phi cube theory or the isotropy. One is you take alpha prime to 0. Okay, so if you take alpha prime to 0, this disk integral give you back the phi cube amplitude in the field theory limit. But which is also just the canonical form of this polytope. So actually, there's a general theorem that for such general integrals, there's always some polytope that controls where the integral converges, and when you take alpha prime to 0, what is the leading order? So this string, the fact that the leading order of string integrals in this case is given by adjoint phi cube amplitude is explained as a special case. But there's also another context you see the appearance of isotropy, namely if you take saddle points of your string integral. If you take saddle points, you recover the scattering equation. And as I said, the scattering equation gives you a map from this modular space to the isotropy. So the alpha prime to 0 limit is also computed by this formula I just gave you, which is summing over all the saddle points in the opposite limit where our alpha prime goes to infinity. So what we found with Nima and Thomas Lam is that this is a rather general phenomenon that for any stringy integral, which also sometimes known as Euler-Melling integral, so which appear in many contexts. I believe it's also what you do. This Melling transform, of course, also appear in the transform amplitudes into celestial amplitudes. But the pre-image of this transformation is different here. So you can view string integrals or finite integrals in the intersection theory context, or more general concepts, more general objects under the same concepts of the stringy integrals. And we found the fact that CHY formula exists for strings is just a special case of this general phenomenon that you can take alpha prime to infinity, which also computes you alpha prime to 0. Okay, so these are the 3 comments I wanna say about general dimension, but we can also go back to special dimension where we see actually things are even more interesting, because now you don't. Yeah, so basically, if you go back to 4 dimension, the one form I told you before, if you write it in a polynomial form, the fact that it's in the light cone can be now expressed as the fact that you can write it as some lambda, some spinor polynomials, which have degree d and degree n-2 minus d. Okay, so your scattering equations now just fall into different sectors. They fall into sectors labeled by d, the degree of your twistor string rational map. Or you can write it as this Voronezh map, which map the from G2n to a GKn, where k is just the d+1. So why I'm talking about G2n here, because the modular space now is not only the Riemann sphere, but you also have this little group variables t. So that's the difference in 4-dimension and in general dimension. Now you start to talk about your spinor variables, which has this t variable also in it. So combining the Riemann sphere with this t variable, you get a G2n, the two planes in n dimension. So now,
sorry, Son, you have 1 more minute.
Okay, great. I'm done in 1 slide. So with this G2n as your modular space, and your scattering equation fall into different sectors labeled by the degree of your map, or the k of your Grassmannian in this Voronezh map formalism. You can now write down, say, in 4-dimension, the original RSV formula for n equals 4 superamuse, also the formula of Freddie, Dave Skinner, and Lionel for n equals 8 supergravity. So basically, here you have a Pactator form, and here you have something called resultants, or the Hodges determinant, as Lionel mentioned in the last talk, a generalization of Hodges determinant, which is the reason that in gravity case, this breaks conformal symmetry. So here you have no dependence on kinematic invariance, which is conformal invariant, and here it breaks conformal symmetry. And you can also go to 3 and 6 dimension to have to have formulas for many different amplitudes in ABJM theory or other theories in 6D. So let's still this is my last slide. Let's still talk about like 4-dimension. What happened to soft theorem? Of course, your general dimension soft theorem now reduced to 4-dimension. Everything still holds, but now you have the special thing that you have helicity and spinors and so on. And this 4-dimension soft theorem is related to BMS, the asymptotic symmetry and so on. So now you really can see that there's this in 4-dimension. The special thing is that you not only have a celestial sphere, you at the same time have a celestial sphere and a Riemann sphere. Unlike in D dimension, you still have the Riemann sphere for your world sheet, but you have a celestial D sphere, not only 2 sphere. And similarly for amplitude relations, there's something special. So everything we talked about is true, BCJ and so on, still holds in 4-dimension. But in 4-dimension, we know there's also we can compute this amplitude using BCFW recursion, using spinor helicity and so on. And it's not obvious to me at all that these formulas help us to do computation in 4-dimension. I mean, for superamuse case, there's some relation, but for gravity and so on, this is all open question, I think. So the final thing I want to mention is that now in 4-dimension, instead of talking about the positive geometry, which is the modular space, now you talk about your positive geometry, which is a positive part of G2n. And then the scattering equation maps you not to a polytope that gives you phi cube amplitude, but to this so-called momentum amplitude. Okay, so this is the amplitude for n equals 4 superamuse that live in lambda tilde space, but you can really see it's nothing but the image of your scattering equation in 4-dimension. So I won't go into detail, but just want to say that we still have a much more complicated positive geometry living in 4-dimension. Now, not for phi cube theory, but for n equals 4 superamuse. For gluons, really for gluon amplitude in 4D, there's a natural positive geometry from the image of scattering equation. But a very, very interesting question is there some string theory here? So can you really view this momentum amplitude and the 4D scattering equation as coming from also some stringy integral? I mean, this certainly has not been answered. Okay, so that's all I want to say. Thank you.
All right, thank you, Song. Let's thank Song for this talk. So in view of schedule, we have only time for 1 question. Do people have questions?
Yeah, I would have one question or comment. So, but the celestial sphere is your Riemann sphere. So it's, I mean, all your solutions of the scattering equations are exactly the points on the celestial sphere.
In 4-dimension.
Yeah, and yeah, it's a 4-dimensional Young-Mills, yeah. So you can check that the points on the celestial sphere are exactly the solve the scattering equations.
Only at MHV.
Only for MHV sector, yeah. So for
No, but,
MHV sector,
no, but it's no, in general, I mean, it's a kinematical problem only. I mean, you have your CIs describing the momenta on the celestial sphere, and then
yes.
you just
I agree. Those ZI solve scattering equation, but they solve scattering equation of the D equals 1 D equals 1 sector, not of other. So the equations have different form for different degree. For degree 1,
okay,
it's
for the
true
MHV,
that the Z solves the scattering equation, but for other degree, that is no longer true. Yeah. So the Z here are different from the Z in the lambda and lambda tilde. Yeah.
So for the MHV sector, in principle, it should be possible to take over your language onto the celestial sphere.
And I totally agree. Yeah. For MHV sector.
I mean, yeah. Let me maybe also, everybody keeps saying these words, but it's important, I think, to do it precisely. Okay, he has some prescription using CHY, and there's a prescription using, celestial. So what is precisely the statement? Just to say, okay, you have a S2 here, you have another S2, they're the same, but one needs to make it
for MHV sector.
Isn't the Riemann sphere a branch cover of the celestial sphere?
That's right. It's a degree K minus
Yes,
1 map.
that's a precise statement. Yeah, in 4 dimension. Yes. But the weird thing is that everything works also in D dimension, where we do not have we have a D minus 2 celestial sphere, right? So in 4 dimension, I agree that this is just cover of
It goes back to RSV. I guess in RSV they had a degree K minus 1 map at n to the K MHV.
Yes.
For the and it was the map to the kind of lambda spinners on twistor space. That's the lambda spinners on twistor space of the celestial sphere. Whereas the sphere of the scattering equations is a degree K minus 1 cover of that.
Yes.
So you can project down. You can always project down onto the celestial sphere, but it's really a branch cover, as Andy was saying.
Mm-hmm.
Okay, if there are no more questions, let's thank Song again, and I guess we move on to the next talk.
Thank you.